Alright, let's continue our discussion of 5.1 areas and distances. I want to look at a visual example of one that we talked about in the last lecture when we were looking at the interval or the area under the curve from x equals 1 to x equals 3 of the function f of x equals 1 over x. So remember that's one of the examples we looked at, x equals 1 to x equals 3. And so I'm going to use this program here, Mathematical Visualization Toolkit. I've used this a couple of times that you may recognize. And this is a free program, so if you're interested in getting this program, please let me know. It's actually a very good program. It has lots of very good stuff on it. So here's our function f of x equals 1 over x from x equals 1 all the way out to x equals 3. Now I've used 4 subintervals just like we did in our example. So number of elements is how they call it here in this program, is 4. And so you can see we are using in this case, the left endpoint. So we have an overestimate since it's a decreasing function. We're taking the function value at the left endpoint of each subinterval. Now the actual area, I don't know if you can read this or not, the true area is about 1.10. This total area approximation is 1.28. That's what we got before. Okay, now if we use right endpoints, well, we have an under approximation. We got 0.95, which again is what we got in the last video when we did this example. And so using right endpoints for a decreasing function, we actually get an underestimate of the actual area. Now one thing we didn't talk about, but we should, is the midpoint. We can also use the midpoint from each section. So if I have these subintervals, the subinterval from 1 to 1.5 has a midpoint of 1.25. From 1.5 to 2 has a midpoint of 1.75, and so on. So if I use 4 subintervals with midpoints, I get the best approximation yet for using 4 subintervals. Here I get an approximation of 1.09 where the actual area is 1.1. And that's usually going to be the case, that the midpoint is going to give you the best approximation. You can see we're taking our function value at that midpoint, and that's going to give us the height of each rectangle, adding those up. And you can see why it gives us a good approximation, because we have a little bit area that is above the curve and a little bit of area below the curve. So we have the errors kind of balancing each other out for these rectangles. But as with everything, remember what happens is we increase the number of subintervals, we get a better and better approximation. You can see that the approximation is getting better and better and better here. Or if you add up the areas under these rectangles, you're getting a very close approximation to the actual area of the function. That's going to be true then with either left endpoints or right endpoints. As the number of subintervals goes up, the approximation gets better and better. You can see here with these right endpoints, we're at 1.09 for our approximation, where the actual area again is 1.1. So, and with the midpoint, we're pretty much right on it. Okay, so there's that example. Now let's go to the next topic in 5.1, and then we'll look at again a couple of examples. That's the concept of distances. Let's suppose that you're out golfing and you got yourself a long putt, and you're able to actually judge how fast the ball is going at any particular moment in time. So then we make a table here. We'll let time t equals 0 be this horizontal, the top of this table, and we'll let f of t be the velocity of the ball at that particular moment in time. Alright, so let's say we have at t equals 0, that's when we strike the ball, that the ball is traveling at, say, I don't know, 40, and that'll be in feet per second. I guess that's moving pretty fast. So you hit it pretty hard. After 1 second, it's traveling at 30. After 2 seconds, it's traveling at 15. At 3 seconds, it's traveling at, say, I don't know, 5. And after 4 seconds, it's traveling at 1 foot per second. So it really slowed down there. What you can do here now with areas under the curve is we can approximate how far the ball traveled for any given unit of time. So we can ask how far did the ball travel from, say, t equals 1 to t equals 4. Well, the way we can do this is we can make a graph. I'm going to make a graph of this function, f of t, which again I'm thinking of as the velocity of the ball. So maybe we should have called it v of t, but that's all right. So let's make a graph here. Now let's see, I think we had 1, 2, 3, 4. How many points do we have for our input? Only up to 4. Alright, and then let's just go by 5, 10, 15, 20, 25, 30. Alright, 1, 2, 3, 4, 5. Now at t equals 0, the height of our graph is at 40. Oh, we got to go up to 40 here. So there we go. Okay, so we have that point right there. At 1 second, the height is at 30. So we're at this point here. 2 seconds, we are at 15. Dropped off pretty quick there. 3 seconds, we are at 5. And at 4 seconds, we're at, I think, just 1. I don't think we had any data for the 5th second. All right, so we were looking for how far did the ball travel between t equals 1 second, so this point right here, and t equals 4 seconds. Well, let's go ahead and connect these dots with a nice smooth curve here. Well, one way we can approximate this is by making a couple of assumptions. So we can say at t equals 1 second, the ball was traveling at 30 feet per second. Well, I'm going to assume that it was traveling at that rate for the full time interval from t equals 1 second to t equals 2 seconds. Well, that means that, how far did it travel? Well, it traveled 30 feet per second for 1 second, so it traveled a total of 30 feet. So what I'm going to do here is I'm going to make a rectangle, and the area of this is going to be 30 because it has a height of 30 and a width of 1. Now at t equals 2 seconds, the ball is traveling at 15 feet per second. So in order to approximate how far the ball has traveled, I'm going to assume, even though I know that's not the case, I'm going to assume that the ball traveled at that rate throughout that entire second from t equals 2 to t equals 3. Well, I can represent that with another rectangle that has a height of 15 and a width of 1. So this rectangle then has a height of 15 and a width of 1. And finally, from t equals 3 to t equals 4, well, at 3 seconds, the ball was traveling at 5 feet per second. I'll just assume, roughly, that the ball traveled that fast throughout that entire time interval from t equals 3 to t equals 4. So how far did it travel in that 1 second with that assumption? Well, it's traveling 5 feet per second for 1 second, so that's a total of 5 feet. And so you can see that the areas of these rectangles here give us an approximation of the distance traveled by that ball from t equals 1 to t equals 4. So our distance traveled is approximated by, well, 30 plus 15 plus 5. But hopefully this illustrates the fact that this area gives an approximation of the distance traveled. The actual distance traveled is going to be, the area under the curve from 1 to 4. So the actual distance traveled is again the area under that curve from t equals 1 to t equals 4. So our approximation was, what, 30 plus 20 was 50 feet in those 3 seconds from t equals 1 to t equals 4. But we could get a better approximation if we had more data. If, for example, we knew how fast the ball was traveling at 1.5 and 2.5 and 3.5, then we could make smaller, better approximated rectangles, which would give us a better approximation of the actual area under the curve. Okay, so the distance traveled we can find if we're given a velocity function and we have a graph of that velocity function, then the distance traveled from any 2 units of time can be found by finding the area under the curve. And that's exactly what you're going to want to do on, for example, number 16. Number 16, I'm just going to draw a very rough graph of what's going on here. You have the graph of the velocity of a car in kilometers per hour. And let's see, we're marked off at 10, 20, and 30. And looks like we're marked off here at 40, 80, and 120. And the velocity function looks something roughly like this. Alright, so you want to estimate the velocity. Well, again, or you estimate the distance traveled during this period from 0 seconds to 30 seconds. So what you're going to do then is you're going to make an estimate. I would do it every 5, so you have some data you can get here at 5, 15, 25. So I would do either right or left subintervals. My graph's not going to match up exactly right, but you're going to estimate it by finding the areas of these rectangles. And the area of these rectangles are going to give you an approximation to, I'll get a little farther here, to the area under the curve, which, as we said, the area under the curve will give you the exact distance traveled by that particular car. So you could use right intervals. You may want to actually do right intervals and then left intervals. Now, if you do left subintervals, your first one is going to be a rectangle of area 0, because the value of the function of the left endpoint of the first subinterval is 0. But then you would have this one here, this one here, this one here, this one here. and this one here. Now the best is probably going to be to use midpoints. That'll give you the best estimate. And those midpoints, in fact, are exactly what you're going to be asked to use. So you are going to want to use the midpoints. If you look at the question, you're going to want to use these areas right here for these rectangles, these purple ones. And I think if you do it, like I said, find rectangles 1, 2, 3, 4, 5, 6 of them, and estimate these areas, you should be in pretty good shape. So, all right, and then lastly, I want to take a look at your last problem in your homework, which is kind of like number 22 in your book, but a little bit different. So it's like I said, similar to number 3 in your homework. You have the function f of x equals equals x cubed, and you have from x equals 0 to x equals 5. So remember that we said we're using right endpoints here. We want to use right endpoints to find a formula for the area under that curve. So remember what we said for the right endpoint formula, that the area A is going to equal the limit as n goes to infinity of r sub n, which is the limit as n goes to infinity of, well, the sum I goes from 1 to n f of x sub I times delta x. So we need to figure out a few things. We first need to figure out delta x. Well, delta x, remember, is b minus a over n. So in this case, this is your b here is 5, your a is 0. So it's 5 minus 0 over n. That's 5 over n. Now what about your x sub I? Well, here's where things get a little bit tricky. Your a value, which is also called x sub 0, is 0. Now what is x sub 1? X sub 1 is going to be your initial starting point plus a delta x. So 0 plus delta x, which is equal to 0 plus 5 over n. Alright, what's x sub 2? Well, x sub 2 is going to be your initial starting point 0 plus 2 delta x's. So delta x times 2, which is 0 plus 5 over n times 2. If we keep going like this, we can see that x sub 3 would be your starting point plus 3 delta x's, 3 subintervals, and that's going to be, well, that's going to be 3 times delta x, which is 5 over n. If you carry this on, x sub I, for some general term x sub I, is going to be 0 plus I delta x's, or 5 over n times I, or we could just say 5I over n. So, putting that into our formula, remember that our area is equal to the limit as n goes to infinity of the sum I goes from 1 to n f of x sub I delta x. Let's just put in what this is. This is the limit as n goes to infinity of the sum I goes from 1 to n f of x sub I. Well, x sub I we just found to be this right here, 5I over n. So we have f of 5I over n times delta x. That's equal to the limit as n goes to infinity of the sum I goes from 1 to n. Let's see, what is f? Well, remember our function f was f of x equals x cubed. So we're cubing what we put into it. So that's going to be then 5I over n cubed times delta x, which, as we said before, is 5 over n. All right, and then from there you want to use the fact that the sum of the first n integers, I goes from 1 to n of I cubed, the first n integers cubed, which is just 1 cubed plus 2 cubed plus 3 cubed and so on, plus n cubed. They give you that formula in your homework to be n times n plus 1 over 2, and that quantity squared. Okay, so if you have your area, which is equal to the sum I goes from 1, well, that's not our area, because let's not take the limit just yet. If we take the sum I goes from 1 to n of 5I over n cubed times 5 over n, we can say that's going to be the sum I goes from 1 to n of, well, now 5 over n and 5 over n, we have a 5 over n cubed. Let's write it this way. 5 over n cubed times I cubed times 5 over n. Now the only thing changing as our index goes from 1 to n is the I value. So I could say this is the same as the sum I goes from 1 to n of 5 over n cubed times 5 over n. So that's 5 over n to the 4th times I cubed, which is, just hang on here, no, it looks a little ugly. 5 over n to the 4th times the sum I goes from 1 to n of I cubed. I goes from 1 to n of I cubed. So in other words, we have 5 over n to the 4th times this sum right here. We can pull that 5 over n to the 4th out front of our sum because, again, nothing's changing in this. This is just like factoring out some factor that occurs in a bunch of terms that are being added together. You can just factor that baby out. And now you got the sum I goes from 1 to n of I cubed, which is this right here. So you can take all of this and put it in for all of this. All right? And then what you're going to do is take the limit of this as n goes to infinity. And so here you'll take the limit of this as n goes to infinity. And you should be able to do that using the rules we've had for limits in the past. And you should be able to get a nice solid number. So good luck with that, and let me know if you have any questions about this homework. The password is ignominious, which means humiliating or degrading. I don't really have any application of that word. Ignominious, ignominious. Good luck on 5.1. Let me know if you have any questions.